Morning, all. Uh, this is the lecture number 2 on analysis and design of high-rise RCC buildings online course. In the first session, we had seen the approximate methods which are there that can be used for the building frames. Going back to that session for first 5 minutes, uh, the things that are required, I'll again go through that for first 5 minutes. My screen is visible to all. So in the lecture 1, we have seen the approximate method. For can you switch off the mic for now? Approximate method, approximate method for analysis of the building frame. In that, we had seen one simple portal frame in which the base is fixed, and in another portal frame, the base is pinned. I had given a problem to solve for SIKI and the SFD PMD for this multi-bay portal frame. Right, so there was a lateral load applied for this. In all these cases, the lateral load is the application. Now, tentative as a qualitative analysis we had to do in qualitative diagram. We understand the behavior of the structure. So one is the deflected shape. So this was the deflected shape for building which is fixed at the base, and the joints are rigid. In this particular case, your deflection is not changing much within the columns because it is a pin connection. It will be a diagram something like this because the joints are rigid, so it will have the double curvature, whereas the columns will have single curvature. So in this case, the columns had double curvature and beams also had a double curvature. Here the column is having single curvature and beam is having double curvature. And we had solved for the SF means base reactions. What are the reactions at the base? And vertical reaction, as it is a clockwise moment, this will be the anti-clockwise moment we have to generate. Okay. So this frame is behaving globally clockwise moment, and the reaction will be anti-clockwise moment. So that is given by the two couples that we have. The same will be here also. Only thing is you will have a bending moment reaction here. It will not be there. So P into H by 4, P into H by 2, that are the bending moment diagram. Then the shear force is P by 2, P by 2. Vertical reactions, you have means this is P into height is H and this is L. Right. So your moment will be P into H and divide by L is the lever arm. So moment is P into H and L is the lever arm. So that will be a vertical reaction like this. That will remain the same here. Yeah. So this was regarding this frame that we had seen, simple portal frame. The SI we had seen, the KI we had seen for this arrangements, and I had asked to calculate SI and KI for this problem, and this is for using the this portal method. We were solving this problem. So assumptions of the portal method were discussed last time. What are the assumptions and how we are doing it for the building frames? So same we have to do it for the larger frames as well. Only thing is now the height will increase. The only difference from the regular textbooks that you use, I had asked you to use the book of Adrian Scarlett for approximate methods, in which they have referred to zero moment point method. So in this, the difference comes out that whenever you are solving the problem using this particular method, you have to estimate the point of zero where the bending moment is going to be in the shape. So in portal method, we are assuming it is at h by 2, h by 2. That is the assumption with the case that the beam is quite rigid. If the beam is quite rigid, there is a chance that it will vary by some margin from the center. Okay. So actually, when you see the bending moment diagram in the ETAP software versus what you will be doing, there is quite a difference in that. That's why you will not get a accurate approximate method moments. So what they have told to increase by 10 to 20% the moments as a without any calculation. However, if you are doing the calculation, they have created graphs. Now these graphs are developed based on what assumption? There is a V factor, that is KB upon KC, ratio of the stiffness of the beam and column. And what happens that in this particular arrangement, your KB was stiff, so case 1 is stiff, case 2 is flexible. So when the beam is stiff, you will get a diagram like this, what I have shown. But if the beam is flexible, okay, so EI is not equal to, that is flexible beam, your bending moment diagram will become like a cantilever, like this, right? So that is 0 point will shift to the above story somewhere here. Okay. That way, these two values are estimated, and based on that, they are calculating the 0 point moment. So first, they will calculate M, and they will calculate M cantilever. This is for particular floors. So this is for each floor. Now your total moment, let's say from this particular height, if there are, let's say, four frames are there. So one, two, three frames, and fourth is the ground. So there are four frame heights. This lateral force has to transfer. Okay. So take it in reverse order, maybe one, two, three, four from bottom. Because in the textbook they have mentioned it like this. Okay. So this is the force P. This is the story height H. Okay. In this particular case, P by 2 will be on this frame and P by 2 will be on this frame, right? So that way, P into H by 2 will be the moment at this point, okay? And at this point, columns, two moments. Now this again, P value will act here. Again, it will give a moment here. Okay, so transfer of forces from top to bottom will take place, same force. So this is for the force which is acting at story 4. A similar process will happen when there is a force at story 3. This is a uniform force arrangement. So there is a formula when the force is uniform, then it is 4 into 3 by 2 into 1 plus 2 up to 4, because the force is traveling from top to bottom. Okay. So that way the force has come out, and this is multiplier for each floor level. However, if the force is not uniform, okay, let's say it is 4 here, 3, 2, 1 that way, then your formula will change. It will be 3 by 2, okay, that is h by 2, into, now first we will multiply by the force into the floor level, plus force into again the floor level, plus that way into floor level, plus 1 into floor level, because 1 has to transfer only one story, while 2 has to transfer to two stories, 3 has to transfer three stories, and 4 has to transfer to four levels. So h by 2 will be transferred up to the bottom. So that way you will get the your M cantilever. So these are the formula for M cantilever. Rest is the same, nothing much it will change. Only thing is this part M cantilever, how the uh, approximate methods in Adrian Scarlett book is calculated. That reflects more similarity with the software results. So one is we will be doing with the routine textbooks. That is a portal method in which the zero moment point is at h by 2 distance, and we will also do portal method using Adrian Scarlett. This is also approximate. Now, second method would be moment distribution method. Okay, so moment distribution method is way better because you can estimate the moment at each joint and then you can compare it with the software. So these way we have two methods. One portal method. In portal method, one is based on routine assumption, and second is zero moment point assumption. And second method would be moment distribution method to solve the portal frames under sway action. Okay. So, uh, so any query, if it is there, I also given the reply to one query raised in the group for approximate method by Adrian Scarlett. Overall, moment distribution method gives a better estimate, which we can use for all our problems too, that we are solving using ETABS. The approximate method for lateral forces, as well as for the gravity loads, we can use the moment distribution method. And another method is the stiffness method, but to generate a stiffness matrix for a 10-story building, it will require additional efforts, which we are depending on the software for that. So with that, yeah. So this was all for the lateral loads. And for gravity load, there is a column area method and beam reaction method that we saw last time. So beam reaction method, if we see the beam reaction method, how it is, that is, you can refer any standard textbook. Like this is a particular slab, and there is a beam B1, B2, B3, and B4. And this is a two-way slab. So this will be the load distribution, let's say. So this is the Lx and this is the Ly. So there is a trapezoidal load distribution on this longer length and triangular load distribution on the shorter length. Okay. So first you have to estimate using this. So which book to refer for this? One is A.K. Jain and another is Dr. Ajisha and another is Shah and Karve. or any other textbook of similar capacity you can also use in which this is given, but these three cover very adequately all these aspects. So you can refer these books to estimate the trapezoidal load and the triangular load coming onto the slab. And once you get these loads on the beam, let's say triangular load you evaluated for this particular beam B1, maybe Q into Lx by 3 is the force, and this is the B1 beam which is fixed at two ends between the columns. Okay, so I am taken a small portion from the building slab, interior slab. So it will be fixed on both ends, and B1 will be the beam with length L and EI. Okay. And from this you will get a reaction, right? Vertical reaction will come, and also the moment reaction will come. These two reactions will be transferred to your two columns on which the beam is supported, right? So it became a frame for you for a particular story. Okay. So this way you can, this was anti-clockwise, this moment will become clockwise. Finally, the reaction will be also like this on the column, right? And this is, let's say, for story number 3. Same will repeat for story number 2 again. So you just have to understand this free body diagram. From beam, the reactions transferred to column, then again reactions at the bottom that will go up to the footing level. There will again come a beam here at story number 2. Again, there is a triangular load of the slab, maybe. Okay. Again, I take it as a B1 if it is the same case. Again, there will be a column here. So there will be a vertical reaction coming here. An opposite reaction will come on the column. There will be a moment, and this will be a moment in the other direction. So that way, you have to keep transferring the moment from the beams to the columns and columns to the footing. So here, whatever the load on the 3 is coming, that will get transferred to the columns also. So that way, you will calculate the gravity load analysis. Now, this is transferring of load. Second is what load to have for the maximum and minimum bending moment, which we call substitute frame method. Right. In undergraduate, we had done substitute frame method for gravity and portal method for the lateral loads and moment distribution also for the sway frames. Same we have to utilize it here. And in substitute frame method, how many internal and external supports are there? Okay, so if you put alternate spans, what will happen that this will bend like this, but this will bend like this. So end spans are always hinged. Okay, so it is not fixed. So this will create a negative bending moment for it. So behavior will be negative. Now the same span, if I keep and load here, what will happen? This will bend like this. This will bend like this. So this will be maximum positive bending. And this will give you maximum negative bending moment for which span? Let's say this is A, B, C, and D. So span BC, we are evaluating. Now, when you go to span AB, this will give you positive and this will give you negative bending moment. So this way, the assumptions in the substitute frame method have to be also referred, in which it is very well covered in book of A.K. Jain and B.C. Punamiya. RCC designed by A.K. Jain and B.C. Punamiya. It is a voluminous book of maybe 800 pages, which I also have and I refer to it whenever it is required. Right. So hope these basic methods are clear. Uh, but means when it is required for you to calculate, you should remember the assumptions. Right now, we are understanding the methods, and from textbooks, you have to practice basic methods, which when we are going towards the ETABS to the real problems, we should not face a hurdle of non-understanding of the assumptions or how these methods have derived and how these methods are successful or not successful in capturing what uh, parameter. Okay, so that is the main intention. Am I audible? Hello, am I audible?
Yes, sir, you are audible.
Okay, okay. So uh, let us now focus today on center of mass and center of rigidity. That is lecture number 2, and this is very important for any building that you are going to plan for high-rise structure. So where the eccentricity between the center of mass and center of rigidity has to be limited, and if not limited, then torsional irregularity takes place. And to control the torsional irregularity, the session was carried out. The video is already in the YouTube and also on my website. So you can go through that video also after today's session. Now, this is again manual method or center of mass and center of rigidity. So today's agenda is center of mass and rigidity, which we call it CM, this we call it CR. And in software also we can check these values. So in software, there are two options given. One is in the response spectrum method when you are giving the definition in the software. Also in the earthquake X definition, that is the static load case. I will say this is the load case in ETABS and this is load pattern in the software. Yeah. So two definitions are there, static and dynamic load cases in which we have to give the center of mass and rigidity. So if you are not using response spectrum method, then you have to define it here. If you are using response spectrum method, then no need to define it in the software for static case because it is taking as proportion of length, not the direct value. So you have to estimate the CMCR, then you have to convert it into relative length, and then you have to give it. If you are doing it for this particular case, that is the static method. So it is a different method than we estimate CM and CR. Just a minor modification, but people find it difficult to put it. So this is the difference in two definitions that we do in ETABS. Now, uh, if my building is like this and my building is like this versus my building is something like this and also it may be like this. And there is a new concept in the market in which the buildings are mostly I-shaped. So it will be more like this on here, this way. So many buildings are right now having this shape in Mumbai. And these are regular cases of L in which they give the expansion gap to separate, okay, two towers. And that way, as the code is not allowing us to use T or L, okay, so there is a expansion gap they provide between the two buildings. So T and L shapes are not there. In many cases, the some cases the buildings are triangular also, like this. So there also you have to give two expansion joints, at least to distinguish the buildings. One building is here, second would be here, so there will be two expansion joints. Okay, so three expansion joints would be required to generate this type of some arrangement. So one is the shape of the building. How is the shape of the building? How to we provide for that? We have to refer IS 1893 2016, which I will just open right now. So in various irregularity cases, it has been mentioned there is a plan irregularity in which the first irregularity is the torsional irregularity that we will go through, and also the video is uploaded, full detailed session is there on the YouTube channel and on my website for well proportioned building. So what is a well proportioned building for this? So stiffness distribution of the vertical elements resisting lateral loads is balanced in plan according to the distribution of center of mass in plan, and the floor slabs are stiff in their own plane. Then it is a well proportioned building. So they have defined what is a well proportioned building. The stiffness is well distributed of the vertical elements which are resisting the lateral loads in the plan. So it is not like a concentrated stiffness point, like only a center core is provided and nothing else is provided. So that building will have first mode as torsion. So what is a well proportioned building where the stiffness requirement is estimated and well distributed on the perimeter as well as internally. That is a well proportioned building. So that is the first line it is explaining. Second point is the floor slabs have to be stiff in their own plane. This happens when its plan aspect ratio is less than C. So plan aspect ratio is the length by width. Now if my slab, this is the, let's say the width and this is the length of my building. So building also has a plan aspect ratio. Now there is a particular slab is also there. And if you have provided an opening in between, let's say, this was the grid in the building, and there is an opening provided here. So I will consider only this portion of the slab where the opening is there. So between this portion, if you are seeing, or let's say some very small grid you created now, okay, there are two beams and in between the slab is provided. So this is a small portion which will act as a one-way slab. This much portion is one-way slab. However, for a full arrangement, okay, global picture, if I am having a slab something like this, in which the length is maybe greater than 10 times the width, so this may be 5 meter and this may be 50 meter, maybe like this, or 45 meter at the most. So 9 to 10 meters difference is there. Then what will happen? This will not act as a rigid diaphragm. So what will happen if it is not a rigid diaphragm? the stiffness distribution of vertical elements will govern. Okay, so each column has a different stiffness. Each shear wall has a different stiffness. Core wall has a different stiffness. So force flow will not happen at the CM and CR values at the CM position. The center of mass will not exist if the floor is not a rigid diaphragm. Then there is no concept of center of mass. Then it will have a distributed mass and the forces will be distributed along the vertical elements wherever they are provided. Like there are 50 columns, then 50 columns based on their stiffness position, the force will get transferred. The core wall is there, so based on that proportion of the area, local area distribution will take place. So mass will get distributed internally within the floor slab rather than concentrated at one point. So the concept of center of mass will not exist if it is not a rigid diaphragm. So it will become a flexible diaphragm, and in that particular case, it will not be termed as a well proportioned building. So what they are saying, if you keep the aspect ratio of the slab L by B or L by B not more than 3, then it is a proportionate size. In both direction, it will be rigid and it will be able to act as a rigid diaphragm. That is what the code is asking us to do in the first 2 points. So are there any queries on these two aspects that are required by the code? For plan irregularity, torsional irregularity case 1, well proportioned building. So if you have any query, you can ask.
Sir, is it only for individual slab or the overall building plan?
Physically, it is a overall building, global picture. So that's why I draw a small portion also. So that small portion can be a local driven action. So locally, the slab cannot be flexible or stiff. However, when it comes to mezzanine level, okay, mezzanine floors, we cannot take them as a stiff or rigid diaphragm. So we have to give it as a either not part of lateral load resisting system if because mezzanine slabs that are only up to 3 or 4 grids, okay, they will not take part in lateral load resistance. So we don't take them as part of LLRS. We don't define them as diaphragms. We take them as slabs. So we will design them for gravity cases, but we will not use them to transfer the lateral forces. So lateral forces will be transferred at story level, not at the mezzanine or the what we say tilt type of arrangement, which is very limited. Locally, 3 columns, 3 ways are there in which the slab is provided. Like I will draw a sketch. So this is the overall building perimeter. Now at some level, there may be a slab which will be something like this. So there will be columns, beams connecting it because slab, the connection will be there. However, it is not assisting in total lateral load transfer. Okay, so we are considering the slabs that are connected perimeter to perimeter. That we will term as a floor. This is a floor, and maybe below this floor there may be a floor like this. So I will not take it as a lateral load resisting system. And when I will apply the lateral load, I will only consider this as my lateral load resisting system. So this will not be given a diaphragm. However, it will be given a rigid diaphragm at this particular level in the elevation side view that I am showing to you, right? So that way, a small portion of the slab inside the building uh, at this particular level, all will behave in a rigid manner only. At this level, we don't require it to be considered. And in some cases, when the aspect ratio is not mentioned, so L by B less than 3, if L by B is greater than 3, or maybe it is a flexible diaphragm. So aspect ratio is just tentative. You have to apply your understanding and ascertain the flexibility. Then you have to take it as a flexible or semi-rigid diaphragm. So you have to first understand what is the given slab arrangement, what is the aspect ratio in plan for the floor and also for the building, both aspect ratio. So either the floor can be flexible or the building also can be flexible, right? So based on that, you have to check uh, this requirement. So is your question answered?
Yes, sir. Yes.
Okay, so these are very defining principles mentioned in the IS code, but it has very means large scale application as we have to follow it in all buildings. What is a well proportioned building versus what is a torsionally irregular building, which is defined in the subsequent clauses, that a building is said to be torsionally irregular when the maximum horizontal displacement of any floor in the direction of the lateral force at one end of the floor is more than 1.5 times its minimum horizontal displacement at the far end of the same floor in that direction. So they have also shown a diagram here. Hope the diagram is visible. That this is uh, a deflected shape of the building under lateral load. So as per the distribution, what I can say is and note something. Yeah. So let us say there was a core wall here. More proportion of the stiffness has come here. So your CR is at this point located. Okay, and your CM is always the symmetry, then it is center of mass in this particular direction. So as the stiffness is regulated more at this particular position, this end will be more flexible. Okay, this side is more flexible, these ends. So we are concerned about the four corners of the building, which will be deflecting under the lateral load. So at this point, as the stiffness is high, it will not deflect more. So there is a delta minimum. And at this point, it is more flexible and it is torsionally flexible building. Then it will have delta max, which will be higher than 1.5 times in delta minimum, right? So this is the case we have to avoid, that if delta maximum is greater than 1.5 times delta minimum, then it is a torsionally irregular building. So that means your stiffness is not well distributed, number one. And number two, your overall system is flexible. That's why your torsion is governing the design rather than the lateral force. Okay, I hope this criteria is clear to you, and I will try to show you through a simple example for CMCR why it is important to ascertain whether it is torsionally irregular or torsionally regular. Right. So proportioning a building, planning a building is very important, and this parameter is very critical for all such cases. So this is the second requirement of the code, that our floor or the building should not be so flexible that it governs in torsion by a parameter 1.5 times the horizontal displacement. However, if I go to the uh, maybe ASC 07, there is a factor in which they call points are the same. However, they call it as a chord. So chord is the straight line. because now the force is acting in this particular direction. Okay, so this is the chord and this is the chord 1 and chord 2. Now this is the CM and this is the CR, let's say. And building has a flexibility to rotate in this particular direction due to the lateral forces. Then what will happen? This chord from its original position, how much it has deflected. Previously, the building was straight like this, a box, and after torsion, okay, something like this happened. As the building is flexible in this direction. So this 0 point you can see in the deflection, right? So this is the radian theta they are estimating, or the deflection they are estimating from this value. So they are using the deformation up to this level, not end to end. Okay, so they have a ratio theta max upon theta average. That is nothing but it is calculating from the 0 point how much the deflection has happened and what is the ratio of it. So theta max upon theta average you will get in the ETAP software also. We are not requiring as per our IS code, but this is a better way to estimate the this torsional irregularity, and they are saying this ratio should not be greater than 1.5. This is what they suggest to use. So we are compensating it. Uh, what we say in IS code, there is no compensation mentioned, but in the ASCE code, if it is a torsionally irregular building, they are using a multiplication factor. So they estimate this multiplication factor and they call it a compensation to be taken for uh, controlling the torsional behavior. So you have a additional moment factor. So you apply that factor to all the moments, and with respect to that, up to let's say factor 3, you can go through that. So once we open AC 7, we can compare the clauses. So how much factor is allowed? Since multiplication factor has to be applied to all the forces, displacements, and then you have to design the building using this compensation factor. So this way, ASCE 7 is defining all these things. However, in the IS code, we have been told that our delta max upon delta minimum, which is at the two ends, this will be delta max and this will be delta minimum in our case right now. So this should be less than 1.5. Otherwise, it is a torsionally irregular building. Now, if it is not less than 1.5, then we have to uh, eliminate this design, then we have to replan our structural system to meet this particular criteria. However, in the ASCE code, up to a certain limit, you can use the compensation factor. It is up to, let's say, 2. So up to value of theta max upon theta average, you can, if it is ratio is up to 2, you can use the multiplication factor. If it is beyond that, then you have to redesign it. Okay. That is difference between ASC 7 and IS code, and ETAPS is using this factor. If you see the table, ETAPS is using this factor. So you should also see the software that what delta max, delta minimum you are getting, is the software doing the same way or not, or it is using a chord rotation. Okay, this chord rotation is from ASC 07, not from the IS code. So that is the first point that we mentioned for it. Now, the natural period corresponding to the fundamental torsional mode of oscillation is more than those of the first two translational mode of oscillation along each principal planned direction. So, it is saying that modal coupling should not take place. In that case, your time period in two directions, x and y. So, x is principal direction x, y is principal direction y. So, principal direction is always orthogonal to each other, that is 90 degree. X will x move, y will y move, not a combined action. So if there is a modal coupling, that will be a combined action. Okay, so in that particular case, you will mostly find a building which is moving in diagonal direction. So in book of this guideline of Dr. CVR Murthy, this is already mentioned. If you have gone through that, you would have understood. So in due to the application of the lateral force, okay, this building is moving in diagonal direction. So this is the feature mostly in square type buildings. These square buildings have similar time period. So as the time period is similar, it will try to move, means have the flexibility in both directions as equal. That's why in action of the lateral forces, it will move in diagonal direction. Okay. So what the code is saying that we should avoid such cases and basically avoid a regular and this square type of building. We should mostly go for the rectangular type of building with good plan aspect ratio and well distributed stiffness. So separate the time period in both directions, right? So if we separate the time period in two directions, your this case will never exist. You will not be able to make square type building. Mostly this case will exist, and you can see your time period will be separate. Now, if your shape is square but you redistribute the stiffness into directions, then also you can get the different time period in two directions. That is also possible. So how you play with the stiffness, how you play with the plan arrangement, and what is the position of the main lateral load resisting element like core wall or in perimeter or in other base, what is the shear wall? If the full building is of shear wall, then how you are distributing the stiffness, also the positions is critical. So once you go with super tall buildings like we have in New York or Hong Kong, so they are mostly square shape. So they are very pencil type buildings. The title is pencil type buildings. So these pencil type buildings are very long but very small aspect ratio in plan. And these are very well behaving in case of provide when they are provided a square type building. So they increase the rigidity in the core and perimeter, and they distribute the stiffness in such a manner that it will not have a modal coupling, right? So that way, this arrangement has to be planned by a structural engineer how it is behaving in what manner. I hope the requirements of the code, four requirements have been mentioned. One is for well proportioned building, two requirements. One is for torsionally irregular buildings, what not to do and what to do have been mentioned. So I hope there is no for if there is no further query on this, we can go ahead. So any query is there? Okay, so we'll take the another requirement. Like in the range 1.5 to 2, the building configuration shall be revised to ensure that the natural period of the fundamental torsional mode of oscillation shall be smaller than those of the first two translational modes along each of the principal plan directions, and then three-dimensional dynamic analysis method shall be adopted, and if it is more than two, the building configuration shall be revised. So if it is 1.5 to 2, this delta max upon delta minimum, then what to do? The building configuration shall be revised to ensure natural. So that is, you play with the stiffness and control the what we say, the stiffness of the building in such a manner that the time period of the x and y direction are mode 1 and mode 2. Okay, and your torsion is not governing the design. That is, it is the third mode. After third mode, the torsion will come into picture, not before that. However, how to achieve this has not been mentioned in the IS code. However, in ASC07 code, they have used a multiplication factor for this type of arrangement. So it is now up to structural engineer to regulate the stiffness of the building and to ensure that the time period is such that torsion is not governing and delta max and delta minimum can be 1.5 to 2. Okay. So though the delta max and delta minimum is more than 1.5, limited up to 2, but the time period is regulated so that the torsion is third mode, not the first mode and second mode, right? So this is a very critical point. So if it is more than 2, delta max upon delta minimum, then we have to redesign everything. However, ASC covers this in a better way. However, we have to follow the code and find a way to get it done. So this was important from CM and CR, most critical part. And next part is yeah, I think this is critical to CM and CR. So this portion we have covered and related torsion, and now we will go to the definition part of it. What is CM and what is CR? So on initial pages of the definition, it is given center of mass, the point in the floor of a building through which the resultant of the inertia force of the floor is considered to act during the earthquake. Shaking, unless otherwise stated, the inertia force considered is that associated with the horizontal shaking of the building. So the meaning of this is that in this particular case, what the code is saying, or in general, whatever the definition of center of mass is understood. So this is a well-proportioned building. So mass is uh, directly at the center of mass. So what is a well-proportioned buildings? That is live load. Then there is the dead load. Then super dead load. Then water tank load. Then machine load. So all these loads are more or less equal along the height of the building. Along the height and plan of building. Like on a one floor, if left side is of the center of mass is heavily loaded and right side of the center of mass is less loaded. Okay, so center of mass will shift to that particular direction. So in which direction the center of mass will shift will depend upon where the mass is concentrated higher in that particular floor. So we are now targeting floor wise and then overall to the building. So in general case, when the loads are roundabout equal at all floor levels, then the CM will be right at the center for this particular plan. Okay, so when we are doing with the other geometry as well, we are actually uh, taking the rectangular shapes, regular shapes. So it will be always at the CG of this geometry if the loads are well distributed. So we have to take one axis, like this is the far end, this is also the far end. So if this is y and this is x, and what is the distance of this particular mass point? There is some, let's say, mass m1, there is a mass m2, there is a mass m3, mass m4. That way, distributed masses are there across the building. So if you want to calculate what is the center of mass in x direction, which we call it x bar, so we have to take that particular mass, let's say this is m1, then m1 into your distance is x1. So what is the x1? This will be your x1, right? What will be your y1? This will be your y1. So now x1, y1, we have this particular mass. So m1 into x1 plus dot 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 mn into xn. Now we have to divide it by x1 to xn. This will give you center of mass for all these things. So what is the first step to do? First step, you estimate the floor mass. Okay. Now it is distributed across the floor. Like there are 8 slabs on the floor. So M1, M2, M3, M4, M5, M6, M7, M8. So 8 masses will be there. Now the CG of so how you distribute between the beams, okay, main spans that is dividing the floor. You will take that chunk of the mass and find the CG of that mass and what is the distance from the x coordinate uh, you will estimate. Okay, so if I am taking, not changing any color. So if there's a slab here, which is something like this, and other slabs are also distributed along the building. So this mass of this particular floor, okay, I am considering, and right now it is not in the CG, but however, this will be the CG of this particular uh, slab, and it will be termed as M1, and distance from X will be calculated. Similarly, for all other cases, it will happen. So now, if there is a, let's say mx, any value, let's say m10 or 11, whatever. If this is a machine load, and if your load is very high on this particular portion, or let's say entire this much chunk is a machine room, So this total load is very high, right? This much portion is very high. So what will happen? Your CM will shift towards the weight which is on the higher side. Okay. So you have to estimate where the CM is going to be there and where the CR is going to be there. So where the mass is high, if the stiffness is also high, okay, then CM and CR will come near. If the mass is high, however, the stiffness is, let's say CR is in this particular position, then your eccentricity will be increased, right? So where your mass is concentrated, where your stiffness is concentrated has to be understood. And CM is the concept when rigid diaphragms are there, when there is a semi-rigid or a flexible diaphragm, CM concept does not exist. The mass is distributed across the floor, it is not concentrated. And based on individual masses, like M1 you saw, okay, in this M1 or M10, where the column is coming, only that much portion will be transferred to the column. If there are three columns here in between mass, like four columns are here, so how much is the tributary area for this mass distribution? It will take local distribution of the mass to those vertical elements. Okay, so that way you have to check whether the slab is a semi-rigid diaphragm or a rigid diaphragm. So as per Eurocode, any slab of thickness more than 75 mm can be considered as a rigid diaphragm if it is continuous. If it is non-continuous, then also if it is not transferring the forces, then it does not become a rigid diaphragm. Like a floor with a very large opening, more than 50%, then you cannot take it as a rigid diaphragm. But in small portion also. Locally or globally, if the opening is very high, that portion cannot be termed as a rigid diaphragm. It will not transfer the forces. So we should not define it as a rigid diaphragm in that particular case. So this way, you will estimate the floor mass and its concentration point, right? So this will estimate in x direction. Same you have to do for y direction. So that is termed as y bar. Many examples are already calculated for this, so that I will also share with you. However, the understanding is not clear for all that how to apply these things in what manner and how to regulate torsional irregularity and how to bring it to the practical level. Okay, so that we are more discussing in this particular session. So this is the basic theory for this and your practical understanding. I have mentioned the loads and its distribution across the height, what is a rigid diaphragm, what is flexible diaphragm, that already the code has also mentioned, and I have also addressed. One is the aspect ratio also is part of it in your consideration. So once this value of CM and CM is estimated, now we can go to the CR. Now to estimate the CR, we should know where the vertical elements are located. So now I will draw the plan of this building, which is quite regular, like this. So case one, that all are columns. It is a, let's say, five-story building in which no shear wall is provided, and all are columns here. Whenever we are dealing with something which is high theoretical background, like in structural engineering, you should have good grip over the assumptions, where and how the theory is applied in practical cases, how we have to use it. Otherwise, there will always be a gap between the concept you just referred versus how what you applied. So this way, this column positions will be like this. Let me draw it here below only. So this will be one, two, three, four, four-story building, and this is G plus four. So that's why it is five. Now uh, we have to estimate whatever the mass is generated at each floor. So we have to estimate it, whatever the mass is there. So that is the case one in which you will estimate M1, M2, M3, M4. Then from this you will what you will estimate for each floor you have to estimate CM4, CM3, CM2. If it is a symmetrical building, then all will be at the center. Okay. So then you can say that at this particular point, all the forces will get concentrated. What the code is saying, CM is the position, right? If I draw the CM in this particular plan, this will be the CM, right in the CG, and your lateral forces will be in this particular point only. So it is a point where the inertia forces are getting applied. So CM is the point where the inertia forces are getting applied, and you have to estimate that point by calculating the floor mass, and you will give uh, this as X, you will give this as Y, and you will estimate X1, Y1 to how many masses are there, right? We will get the center of mass, and you will get so you will get the mass, you will get the coordinates. From that, you will get center of mass. And this is the point where the earthquake forces or the lateral forces will get applied. However, always the CM and this lateral forces are applied at CR. Let's say the CR is at this particular point, center of rigidity. So theoretically, it is to be applied at CM. However, in actual, it is applied at CR in your model. Now, there are two cases to take it. Number one, which is the very logical way, you have to shift CM to CR. So ETABS also has option in it available. So you can shift this CM to this position, and CM and CR will coincide. There is no necessity to estimate the eccentricity, right? This you can do in the software also. Second, you estimate eccentricity. Now that is a static eccentricity that we call ESI. Okay, that is the difference between CM minus CR. It is never CR minus CM. It is CM minus CR. Is it correct? How? What is the formula for this? CM minus CR or CR minus CM? How it is generally estimated? CM minus CR or CR minus CM? So it is this formula CM minus CR to be followed. If CR is higher, this will become negative. So ESI is CM minus CR for that you need to estimate the CR. Now, how you will estimate center of rigidity? It is estimated based on the stiffness of vertical elements, right? So if it is a column K or whether it is a shear wall, there is a formula 12 EI upon H cube, based on which the stiffness of the vertical elements are estimated. Now again, same you have to do. You have to again create X and Y for this particular building plan. That we had just drawn above. So again, for each column, in this particular case, again you have to estimate your X and Y. So for this is the column, let's say K1, you give K2, K3, K4, then K5, K6, K7, K8, K9, dot dot dot. How many number are there? You can give. Now, if it is the same value of K, then it is good for you. But we generally get Ki. So E mostly is constant. So we take I, in which it can vary. Okay, and Hi cube. So in this particular case, you have to check what is the distance of K1 from X. So all these K1, K5, K9, this particular direction, you will get a X1, or let's say X value, Xi value, and this particular you will give again Xi, and this will be again your Xi. Same for Yi, for this particular row, for this column there will be a Yi, for this column again Yi, then if you go on based on the rows, you will get the Yi values. So K1 into this total up to this, you have to consider, right? So that means K1 is at right at Y, so your this Y1 is equal to 0. Now at this position, your Y1, your Y is equals to some value, Y value, Y value, Y value. Here at this portion, the Y will be 0. So Y equal to 0 at this portion. In this particular column direction, your X is equal to 0. Okay. So that you have to take care. Rest you will get some XY coordinates. So here there will be XY coordinate, here will be XY coordinate. So that way you will get those values. Along x-axis, along y-axis, x and y will be equal to 0. So now you have estimated the k value. Now you have to use the formula in which it is k1 into the r. This was x bar. So we can call it as x cap as such. And then k1 into x1 plus dot 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 kn into xn divided by k1 up to how many numbers are there, kn. So this way, you here you had seen that it is not divided by mass. So is it to be divided by mass or is it to be divided by x? That is, I just wanted to. So is this the values written correctly or is this the written wrongly in the denominator of center of mass? This is the formula.
It's actually It's actually the mass is divided, no? The total mass is divided.
Are you sure?
Yes, yes.
So it should be like M1 up to Mn here.
Yes, sir, that's why I'm just a bit confused with the if we like X values.
Sorry, you are what? Okay, so
I think
I have also
hmm,
opened the this explanatory examples by IIT Kanpur. Okay, so we'll go through that. So first example they have given for estimating the lateral force, in which they have estimated the mass at each floor multiplied by AH. They got the base shear, time period, and they distributed the force along the height using the formula WI square upon sigma WI square. So very basic uh, problem is solved in the first case. Then there is a dynamic method to estimate the base shear. So static method, dynamic method, in which the what we say modal mass is estimated, modal participation factor is estimated, and based on the weight distribution and your stiffness and also your modal coordinate, right? Modal displacement. That is a modal vector. Okay, so modal vector gives you the displacement means normalized displacement vector is this, and stiffness is also there. Then you get the time period, modal mass distribution, all those parameter will come into picture. Now, this is the formula to estimate it. Basic, fundamentally, we can let's say understand from here that static and dynamic there is a lot of distribution change in the story shear and also distribution of the story forces. So your total base shear estimated is 1303 kilonewton, and in static it was estimated as 1440. So 1343 and 1440. Base shear. Oh, here it is 1303 and 1440. About 100 kilonewton difference in the base shear is estimated. Also, across the height of the building, the distribution is very, very different. In dynamic, which is scaled, and it is static force. Now, story shear static is this one, which is 611, and story shear dynamic also it is a scaled like static to dynamic. The scaling has taken place, and story shear is coming to be like this. And story moment is also different, and overall there is a lot of difference in your final result in displacement also. So that has been clearly mentioned. Now, location of center of mass is the third problem in given here, in which the mass is distributed for this same floor in different kgs. You can get EM and CR, in which you can see basic formula that is used here. So mass of part I is 1200, something like that. Okay. So now 10 by 4 is the span, is the plan size, and 1200 kg per meter square. So what they are doing 10 into 4 into 1200 kg per meter square. So they are converting the meter square into your kg, which is M1, then 100 into 4 into 1000, which is 10 into 4 into 1000. Again, that is the same, this much portion they have added. So this is your M1, which is estimated in kilonewton. This is your M2, and this is your M3. This is how they have estimated it. Now here you can see in Y1 also 10 into 4 into 1200, 10 into 4 into 1000. So 10 into 4 into, so they have this floor load is converted into kilonewton, right? And multiplied by the ordinate and divided by mass. So basically the formula is yeah, more formula. What is the formula in this particular denominator? That it is actually mass M1 up to your Mn. Here also M1 up to Mn. So this way the mass is estimated. So now how the mass is estimated we have seen, and what is the formula? Now this is for the CR, center of rigidity. So stiffness into ordinate divided by total stiffness. That will give you CR. And the same way X and Y ordinate you have to estimate. So once you, so there were two methods that we were seeing how to uh, means consider CM and CR. So two ways, either shift CM to CR or estimate the eccentricity. For eccentricity, you calculate this difference between CM and CR. To estimate CR, you need stiffness values and ordinate values. And for CM, you need the mass value and the ordinate value. Now, once you have CM, CR value along with you will estimate number one, your static eccentricity. So software also gives you these values and you have to estimate manually as well for each floor. So per floor, this exercise has to be done. Now, second, you have to estimate accidental eccentricity. So to eccentricity, to estimate your design eccentricity as per IS code, you need two values which is equals to 0.05 of either B or L. So in which direction you are considering, you have to take the width. So opposite direction you have to consider. So if the length direction is L, width is B, you make it opposite, then your L and B will become alternative. Okay, so you have to estimate the width of the building. So 5% eccentricity we are considering due to construction. Okay, so 5% is the accidental eccentricity we have to use. So in response spectrum case or in the static case, you have to give this factor 0.05 as input. Okay. Now, once we have these two values, we have EDI formula that is 1.5 ESI plus 0.05 of B. And other is ESI minus 0.05 of B. So what is the worst case? We have to estimate from both and we have to design the building for the worst eccentricity. Okay, so we will again go to IS code, right? And this for this understanding of the CM, CM is the position where the inertia force is concentrated is one thing versus you can shift the CM to CR. So in both cases, inertia force is concentrated on CM. So either by eccentricity or by shifting the CM point to CR point, we apply the inertia forces at the CM. Now, center of resistance for single story building, it is the point on the roof of a building through which, when the resultant internal resistance acts, the building undergoes pure translation in horizontal direction. No twist about vertical axis passing through the CR. So what is the definition of CR? So CR is the point on each floor or on the uh, roof slab, if it is a single story building, that resultant internal resistance develops. So all internal resistance is concentrated in CR. So whatever is the capacity to of the vertical elements to take the lateral force is concentrated at CR. And it is the point where no twist occurs. Okay. So it is the point where there is no twist occurring. Okay. So that is the definition of CR. I hope CM and CR definitions are clear, right? For multi-story building, it is a set of the points on the horizontal floor of a multi-story building through which, when the resultant incremental internal forces across the floors act, all floors of the building undergo pure translation, either X or Y, in the horizontal direction, and no twist about the vertical axis occurs. There is no twist acting at this particular point. Okay, so that is CM and that is CR. Now, the difference between CM and CR is the eccentricity, which we have to estimate as per the IS code. In eccentricity, there is design eccentricity. It is the value of the eccentricity to be used for floor I in calculation of design torsional effects. Design for this difference between the CM and CR, we have a design eccentricity factor, and this design eccentricity is combination of the static eccentricity and accidental eccentricity. So, is the noise very loud? Background noise? Hello, hello.
Yes, sir.
I- Yeah, is the background noise loud and am I audible, or there is some construction work going on top floor?
Nothing, sir. No, no noise is coming. It's clear.
If I am not audible, just let me know.
Okay, sir.
Okay. So for design eccentricity, there are two parameters that I told. One is the static eccentricity, ESI, which is a direct difference between EM and CR. So it is also mentioned. It is the distance between center of mass and center of resistance of floor I. So at each floor, CM and CR distance difference you have to find, which is termed as static eccentricity. Okay. Now, once static eccentricity is there and accidental eccentricity is there, based on the formula, we will estimate the design eccentricity. And based on the design eccentricity that we put in the software. Okay. So whatever design eccentricity values you have obtained per floor, you have to input in RSM load case. In response spectrum method load case, you have to input these values floor wise in the table. Okay. So this is for response spectrum load case. Same you have to do for the static load case also. So that we will also see in the software. So that is a calculation estimation of CMCR. What is the significance of CMCR? The torsional forces get estimated from CMCR. So how much away these two points are there? That is center of resistance, center of mass. More the twist will take place. You have to control torsional irregularity as per the clauses. You have to distribute the stiffness uh, well proportioned in the building, not just concentrated at one point. And your time period has to be regulated in two directions. Also, the time period of the torsion mode should be in the third mode. So you have to control your stiffness in a manner and the pressure in the manner to achieve these criteria as mentioned in the IS code, which are pro to earthquake resistance. Otherwise, there is always a chance that the earthquake may means, overpower the resistance of the elements and the cracking will happen. Uh, this we call it as how we transfer. Yeah. So how we transfer these forces. It should be acting here.
Sir, your voice is not audible.
Voice is not audible or noise is higher.
Sir, uh, for last minute, it's not audible. Noise is
Okay,
not coming, just it's not audible.
okay. So this is a base here which is acting on the CR. So basically, it should be acting at this particular point here. So we have to transfer the force V to CR. So we will get transferred here, but along with that, there is a EDI. So this force will generate a moment equal to V into EDI. Okay. So this is the way the force will get transferred from CR to CM. So it is now acting on the CR, to which your force will. So this is how we take it. You shift the CM to CR position, then moment is not generated. Only thing will happen is you have shifted CM point over to CR point. So this point is shifted here. So now lateral force only will act here. Okay, so two cases how to apply the lateral force. One is you transfer the forces from CR to CM, or you shift CM to CR and lateral force only we will act. There will be no moment acting. But overall, a moment will get generated in the system by itself in the analysis, right? So this is the two cases we have in the software, or let's say in general, to consider. So I hope the code clauses, code requirement, understanding of the concept CMCR, how we have to apply the formulas and for each floor and for once we estimate the forces, how to means estimate for the let's say mm, what we call it for the real buildings, delta max, delta minimum, then delta max, theta max, theta average for the ASC 7 code and IS code. That has to be checked for each floor. So highest worst case we have to check delta max and delta minimum at each story, right? So any query on the requirement to be taken by the structural engineer? Is any more query you have on this, or you understood each segment of it? So what points we have to consider? We if we list it out, okay. So always you should have a checklist initially. Then it goes to your mind. Then you can relate to all points. One is the plan aspect ratio, right? That is the requirement of the code as well. Then there is a diaphragm action, whether it is a rigid diaphragm or semi-rigid diaphragm. Third is your calculation of time period and its separation uh, in translation into principal plan directions. Okay. So instead of calculation, I would say regulation of time period and its separation in principal plan direction. Also, regulation of torsional mode as the third mode. Okay. So this has to be done by regulating your stiffness and planning it properly. So what this requires is your stiffness distribution, then building structural planning. So two segments are very critical in this. Once that is done, you will calculate center of mass, then you calculate center of rigidity. From that, you estimate design eccentricity, okay, which we call it as EDI. Positive and negative, both eccentricity you have to consider. Now, once that is done, you have to estimate your delta max on delta minimum less than 1.5. However, if it is 1.5 up to 2, then you have to regulate time period as above mentioned. Okay. Then, if it is more than 2, then redesign. Right. And this was related to that. And is CMCR torsional forces. Yeah. So design for the torsional forces. So this is the what I can say. Job of a structural engineer. Clear in plan the CM and CR values. Am I clear? Now Understanding part I have completed. We will go to an example and solve, see how in the book it is solved. So for next 15 minutes, we will focus on this approximate method in which the solved example is given that I have shared by Edwin. So this is from that particular textbook. So torsional forces, so by Link's theory, the torsional forces in the space length are estimated. Okay, the, the relative displacement of the slabs. So here you can see the relative displacement of the slabs J plus 1 and K can be resolved into two components. So at two particular floors, I have a relative displacement. So this relative displacement is related to what? Now a translational parallel to the given forces accompanied by translational forces and stresses. So that are the lateral forces and actually lead to higher displacement at the above story than the below story. That is regular lateral force. Then additionally a torsion, a rotation about a vertical axis passing through the center of rigidity accompanied by additional torsional forces and stresses. So addition of torsion forces with the lateral forces lead to higher relative displacement of the stories above than the below story. That is a relative displacement. Now for that we have to estimate CMCR, that is already there. Moment is V into eccentricity that we have seen. Okay. Now if this is a particular plan, I would like you to solve it yourself. Okay. It is already solved. You can also solve. So there is a core shear wall at this particular point. Then there is a perimeter shear wall given. Internal columns are there. Force V and CMCR is to be estimated. And this is the basically exercise we have to do every time we are planning the building. So CM and CR, the formula is given. Okay. Load is distributed along the height. The formula is there. That is, they have considered the weight into X and weight. So from the mass, they have considered weight. We can directly take the mass also. So generally, we estimated all values in terms of the weight, not in terms of the mass. Okay. So that way, it has taken a weight. So ratio of the weight ordinate upon weight. That way, that is the center of mass in X direction. That is X R Y. Sorry, X M and Y M. And now, as per CR calculation, they have used this particular formula sigma I xi into ki plus I xi into. So they have used I values, and what we are using k values. That is small difference in this particular calculation. So if we see this particular case, sigma I xi into xi, where I and Iy are the moment of inertia of the columns. For definition of moment of walls, they are taking Ixa, Ia, that are the shear wall I value, and for the beams here, they are using B. Okay, so if I zoom in more, so Ixa by I by A. So for the column, I they have taken, shear wall I they have taken, and for the, let's say, if the beam is also there, then they consider for beam as well. Our formulas are not that exhaustive. However, this is taken in more refined manner than we are doing. So C column, they have estimated all these values which we are taking K values. They have taken I into xi square. So this is taking like lever arm. So lever arm square into I value. Lever arm square into I value. This is for the column they have taken. For the shear wall, they have used this. But you can refer the uh, example that is available in this IITK manual, in which for the shear walls, also they have estimated, but they have done using the stiffness of the shear wall. However, the distribution of the shear wall is with respect to R. Now, this R is the distance of the shear wall from the CR. So what is the distance of this shear wall from the CR? What is distance from the shear wall with CR is represented by R. So lateral forces in the walls due to torsional moment. So for wall 1, I have to estimate then K into R divided by K of total into R of each. So K into R total is in denominator, K into R is numerator. That way I can estimate the forces. Like if I show you here in this particular arrangement, if this is the building and this is the shear wall and this is my CR, then there will be a distance and there will be a stiffness. So I call it a R, I call it a K. Then your force distribution, and there is wall like this here or here. So I make it as a 1, 2, 3, 4. Then your whatever the lateral force is coming, how it will be distributed, okay, in both directions. That is to be estimated. So this will be equal to we want force in this particular shear wall 1. The force in 1 will be K 1 into R1 upon sigma K into R into your base shear total. So you will get your value F1. Similarly, you will do F2 for getting in this particular direction. You will get F2 value, you will get F3 value from minus. So F3 will be equals to V minus F1. This way you can estimate the shear forces that are going into the shear wall or the column also. So how many columns are there? How the load transfer is getting take place for this arrangement. So location of center of rigidity, then distribution of the lateral forces. So I will add one more point into this particular diagram in this particular job list that the last point would be like estimation of distribution of lateral force ratio. Let's say storage here in vertical elements. Okay, then your task will end once you estimate it because after that you have to design for the forces. Then so in wall AR, let's say A, wall A, what is the force? A into K, F into ED. So that way, for each wall, you can estimate the lateral force, and you can design the wall for that provision. So lateral force distribution as per new torsional provision remains the same. This is also the same. So this is the same way we have also considered. So wherever there is a mass is getting disturbed, if maybe mass is more on one side, mass on the other side, stiffness has to be regulated, and all these parameters have to be ensured. Right. So any queries on these all these particular systems? Also, you refer to the lecture uploaded on my YouTube channel on the website. If you want regularity, you but please do basic understanding. So,
Sorry, your voice is not. Um,
hello, am I audible?
yes, sir, yes, sir. Now it shall.
Okay, so I'll share again. So this is the main aspect that I wanted to cover in this session. That what is the job you have to undertake as structural engineer, following the requirements of the code. Also, understanding of the concept of CMCR, how it is applied theoretically, and how we can apply it in our software, and how to see from the software that I will cover in the next session. That is, we have a ETAP detailed ETAP session. We will go through all these fundamentals again in the ETAPS model when we reach there. So any queries on CM and CR? So I hope you are clear that what you have to follow as per the IS code, what is plan requirement of the building, what is vertical requirement of the building, that is all irregularities are to be considered. We will see more irregularities in a dedicated session of irregularities. So vertical irregularity, plan irregularity, soft story, all those things we will cover in irregularity session. But torsional irregularity we have covered in this session. And all those things we have to consider in CMR CR estimation is very critical for that particular reason. The software is estimating it, delta max, delta minimum ratio. You have to estimate because software is not giving that, and you have to judge whether it is torsionally regular or irregular. So that is for today's session. If you have any query of the last session also, you can ask now. The moment distribution method you should know in detail. That is what I want to say. If you have any queries on moment distribution method, and what theory you have seen in CVR Murthy's literature. If query is there, you ask me. Okay. So anything you want to say before we end the session? So Faisal, are you there?
Yes, sir, I'm here.
So you got the understanding what we have seen in the session today.
Yes, sir, I got the understanding. I need to, watch the previous lectures as well, as I was not available in the last, you know, last week. So
Yeah.
I just completed one lecture, lecture one, lecture zero, I think. I need to, watch the lecture first, and then this is clear, sir. This one.
Okay. Okay. So lecture zero was on approximate method, just introduction of it.
Yes, sir.
So my idea was that too, you should know what are the assumptions in approximate methods.
Regarding this,
And
sir,
well,
the
yeah.
concepts we learned today, where can we refer to, which book can we refer to learn these concepts like plan, aspect ratio? I want to read these concepts.
So plan aspect ratio, basically nowhere it is mentioned. No textbook covers except architecture. But IS code has told to have a plan aspect ratio of 3 and 5. So for tall building code 16700, if you see the plan aspect ratio is, let's say if it is more than 5, then we consider it to be a flexible building, and we should now means consider tall building all criteria for that. And plan aspect ratio for the shear wall and column is 4. Like if not plan aspect ratio, but aspect ratio of the height versus size of this length of the shear wall, that if it is less than equal to 4, then it is a column within the particular story, not overall. And if it is more than 4, then it is a shear wall. This is the aspect ratio for shear wall. Then plan aspect ratio for the floors is to consider as a rigid diaphragm is it should be less than 3. Like x and y direction, the aspect ratio should be less than 3 to consider as a rigid in both directions. Otherwise, we will not be able to take it as a rigid diaphragm action. And yeah, only these aspect ratios are available for this particular way. And height of the building versus the base dimension also is limited. Uh, so whether it is a flexible building or whether it is a shear building. So the behavior of the building is either shear. Shear is related to mostly the bending is not the governing design case. Mostly shear forces are governing, and hence the building is not acting as cantilever. Okay. Now, if it is a tall building and if it is acting as a cantilever, okay, so it is flexible building. So high-rise buildings which are small in plan, larger in height will behave like cantilever. Whereas for a building which is a smaller in height and more in plan will act as a shear behavior. So this way, many different literatures are there, textbooks are there that use this. You can refer the book of Paule and Priestley, Park and Polly and Nigel Priestley. So I will upload those books also, and whatever queries you have, you can put it in the Teams chat. I will respond to it in Teams. Okay. So all queries I will respond on that.
Okay, sir. Thank you, sir.
Okay. So I think we can end the session for today, and please refer this my YouTube video on torsional irregularities to reconfirm or get in more details how to solve this problem in that particular video is also mentioned. Okay.
Sure. Okay, sir.
So Srinivas,
Yes, sir.
Any queries are there?
From my side, no queries.
Okay,
Thank
okay. So try to solve a few problems because in the software, once we go na, we will go fast in the software. Then there will be no chance to get back to the assumptions, to the requirements of the theory, code, all those things. So you should be very intact with theory and code. So when you have to solve a problem, we open the software, we'll solve the problem, right? It is a calculator for us. So what happens when we directly jump to the software, we forget everything else. Then our focus is software rather than outcome of the software rather than the concept. Okay, so I want all to have a very good conceptual background before we jump on to outcome of the software. So then you can dictate whether the outcome is correct or not correct, or what should have been in the first place we should have done so that this problem would not have occurred. Okay. So there should not be a confusion once you open the software. Okay.
Sir,
So we
and
will,
I have one
yeah.
more query, sir. A general query. Basically, we started from this earthquake load, right? The horizontal loads. So we did not learned about these vertical loads like gravity loads. So do we need to uh, do we need to have those topics as well in this course?
Yeah, see, why I have not included for gravity load till now, I have included for beam reaction method is the gravity load, and the column area method is also the gravity load analysis method. Then substitute frame method that we saw today. So three methods are there. Substitute frame method, and then there is the beam reaction method, column area method. Okay. So for frame
Yeah.
analysis and moment distribution method. So four methods we use to solve problems for the gravity cases, and moment distribution method also we use for lateral loads. But my particular attention was towards approximate methods of the portal method that we are using for lateral load. Okay. So there is some approximate method in given in one of the textbooks that covers everything, including the shear wall also. Okay. So what happens is nowhere else these topics are covered. And I assume as you have gone through the undergraduate and postgraduate course, you would be having some idea on the gravity load cases, how you solve
Yes.
using these methods. So that's why I'm not focusing much into that part. However, the assignment is for you to estimate it for routine cases. And if you have any query, you can ask within the week that I have tried to estimate for 3-story building or 7-story building or a 10-story building. And I am facing difficulty at this particular point. So I will cover this, all that also, because covering entire textbook will not be possible in any course. And uh, most of the parts will get skipped because we will be just focusing in solving one problem. However, the requirement of the concept would be a larger thing. So basically, once you are okay with the concept, conceptual understanding, assumptions, application, requirements, and frame, like building frame, what is stability, what is unstable frame, what are end restraints, what is the deformation criteria, what is the how the flow of forces are taking place. Once that is particularly clear to you, okay, methods are already mentioned in many of the books. However, the understanding gap is always there. So repeating what is given in textbook, I will be just repeating what is in textbook. Rather than that, what I am trying to do is the textbook part you can read and we can discuss it faster in the session and use focus more on the higher requirements as a structural engineer. Okay. So same problem in the textbook, I will be solving it here. Will be just repeat of what is already there, right? The substitute
Yes.
frame method is not developed by me or anyone else. You can directly refer and solve a problem. And wherever the difficulty is there, you can put it like, I have taken a problem and I am facing this difficulty. I have uploaded a problem also in the MS Teams for 8-story building. You can break it in 3-story also and solve it manually. And also for 8-story buildings, solve it manually. And then for gravity case, also for lateral case, like there is a simple mass to be estimated, stiffness to be estimated. In static method, you have to multiply by VP into AH. You will get base shear, then distribution along the height. That is the analysis you have to do for that particular case. So all these things that are already there and very well documented, very well explained in IIT guideline also, that we will cover. We will not eliminate that, but covering more sessions on that, because solving each and every floor will take more time. The concept will get diverted. Rather, you at least have some work done from your end. Otherwise, what will happen? I will cover. Okay. I know already what all things are there. You will not be clear that once I modeled this frame, okay, I applied this load. Now what to do next? Once you are yourself putting it on paper, you will understand that what is to be done. So
Sure, sir.
we are going to cover it, but I expect some homework based on UG, PG, what you have already gone through, what textbook already is available, very well documented in NPTEL or the IIT guidelines. That basic understanding should be there on that. Now, when to apply it, how to apply it, in one manner to apply it, how to check fast, that things I should discuss and focus more on to that. Right. So I expect you
Okay,
to
sir.
solve a problem within a week and continue it till the end of the course. So what I have uploaded in the MS Teams, you can use that for entire course as well. You can add shear wall in that, you can add core wall in that, you can apply lateral force or various seismic zones, and that way you can solve multiple problems uh, during the week. Right.
Right, sir.
So we will be covering all these methods as such. However, to cover it fast, if you have some understanding before the session, it will be better. That is the only thing I wanted to say. So gravity as well as lateral both has to be covered. So bending moment diagram, how the diagram is there, uh, that is very important to that. All those things we will cover in our sessions. Okay. Okay. So let us meet next week, and I'll upload the required documents to be referred and what problems to be type of problems to be solved. I already uploaded a problem. You can open it in eTabs and just see the slab thickness, column thickness, beam thickness, beam sizes, uh, and do a manual analysis for that. By the time we cover it in our session. Yeah. Okay.
Okay, sir. Thank you, sir.
Yeah. Thank you. Yeah. Bye.
Bye, sir.